So in this experiment, you've seen that the position of the fish or the angle at which you were seeing the fish did actually matter. Well, does that have any practical implication? Maybe not so much to us now, but it actually did a lot for people in Stone Age times. So for example, if you wanted to hunt a fish, then as shown in this picture here, you seem to be looking at the fish. You have the impression the fish is over here and you're trying to spare it to have some dinner, but in reality, the fish is here. So of course, if you train a little bit, you will learn that you have a bigger chance of hitting the fish by pointing your spear more downwards, because that's the position where it really is. And so the laws of refraction actually allow us to calculate where to point our spear when we see the fish here. So the next phenomenon I'm going to introduce is the rainbow. So this everybody has seen already. However, there are few people really understand how it comes to be that we see such a thing as the rainbow. So the first thing you have to notice is typically on Earth we see a rainbow in this shape, but in reality it's not only a rainbow, it's just that the lower part of this circle is blocked. So you can really, one should speak of a rain circle, and you see that nicely if you're flying in an airplane and passing next to some cloud of rain, then you really see a round rainbow, and you see that this is really a round ring rather than just a bow. Of course, there's barely any water between our point of view, a little bit, let's say 1.5 meter above the earth or something, to the downside, because then we are hitting this here, the surface of the water, or the concrete in other places. But if you're up in the air, you can really see, you can have access to the drops in midair that cause this phenomenon. But how do they do that? Well, so how can we explain such a beautiful effect like the rainbow? Well, first of all, let's look when we see a rainbow. A rainbow can only be seen in the morning and the afternoon. What is the reason for that? Well, you have to have your sun in the back. As you see here, there's a person standing there with the sun in the back, and the light rays from the sun traveling pretty much parallel travel in this direction. And then you have water droplets in the air, and the water droplets have all kinds of effects of refraction, like shown here, and reflection. To explain the primary rainbow, you need to think of a single reflection and two refraction effects. When the ray basically enters the water droplet, it changes direction, it gets reflected at the back and changes direction again. But is that enough to explain the rainbow? Not really, because of course all the different rays that hit in different positions here would have equal probability to hit somewhere, and they would basically give you a mess of directions, and that would just mingle up the light, but white light would still mix to white light. So why do we see a rainbow? The interesting effect is that there will be an extremal position. That means when you look at all the different input rays that are parallel, that come different directions, there's only one extremal output ray direction, and that's why the light sort of concentrates at a particular direction, and we will follow that effect now in the next slide. We'll understand that better. So here's what happens. This is the anti-solar point. That means the sun is coming from the left here, pointing straight to the right. And now let's see what happens. If we point red light in this direction, it will leave at a particular angle here. If we point it in the same direction, but at a different position of our droplet, so this is the model of our droplet, it goes here, and then it goes here. So what you've seen is the angle towards this normal is first increasing and then decreasing again. And this gives this extremum position, and that makes the eye perceive red light along this direction. Now, interestingly, these are other rays, and they're sort of all over the place, but only one extremum here. If we now take a different color, green, you see that this, because of dispersion, that means the refractive index, is dependent on the color of the light, we get a tiny little bit of a different angle. So instead of 42 degrees, it is 41 degrees near the extremum. And that, of course, is then the reason that we see different colors in different positions. So you see here the same phenomenon of extremum, just at a slightly different angle because it is a slightly different refractive index. So this effect of extremal position of the perceived light we will now explore in an experiment.